Hi, I'm Ray from BioBase, and I want to show you how to do some powerful yet simple GIS analysis of bio-based vegetation outputs, specifically how to create plant height maps and depth to the top of the plant canopy maps. Two different ways of analyzing traditional bio-based vegetation data to help answer aquatic plant management and research questions. So first, let's visit the demo account on the BioBase homepage. It's biobasemaps.com. This is a great resource to get sample data sets and get familiar with the kind of data BioBase produces and how to analyze it. So we're going to go to the dashboard here and then click on trips and merges. We're going to download one of my favorite data sets, Orchard Lake, analyze edit. We're going to go into the trip viewer and we're going to, once it loads here, we're going to go to the export feature on the left side here. There's a tools menu. There's a range of tools available, and we're going to go to export data, and we're going to export the CSV data. The CSV data is it is GIS data. It's in the WGS 84 global coordinate system, latitude and longitude in decimal degrees. And these are, we can export the interpolated grid data. So we're going to export depth first, hit submit. It goes to our downloads folder. We're going to rename this GUID to something we can recognize. Okay. And then we want to do the same thing with the vegetation data. Okay. And then we're also going to rename that. So that's all we're going to do in BioBase. Now we're going to jump over to QGIS. And we use QGIS because it's an open source, it's a very powerful GIS and an open source platform, but a lot of you may use Esri's GIS as well. It's a lot of the same functionality. It's just a different UI, and you find the features in a different area. So we are going to add those layers. We're going to add a delimited text layer. Add layer. Delimited text layer. We navigate to where that is. It's in our downloads folder. So we're going to open the depth grid first here. One of the things we want to make sure is that our data is in decimal. That is the case here. We're using the imperial units. Another thing that we're going to look at, if it's not selected automatically, is that projection, sometimes called CRS, sometimes called EPSG. WGS 84 is the 4326 is the code. So everything looks good here, so we're just going to hit add. There you can see the data are added, and now we're going to add the biovolume data. Hit open. Again, we want to zoom over here and look to see the biovolume data. For some reason, it's coming in as a text field. We want to change that to a decimal. So that looks good. And we hit, everything else looks good, and we hit add. So we close that. Now we want to let's get a satellite imagery background, see where we are in the world, and just ensure that we have that our projection is right and that things line up. So we're going to go to this XYZ tiles feature, and we have Bing Maps loaded here. You can do a Google search if you don't have these by default. You can do a Google search on how to load Bing Maps, XYZ tiles, and QGIS, and it's pretty easy. So we're going to add Bing because Bing is the aerial or is the satellite provider that we use in BioBase. And we're just going to put that down here. And now you can kind of see how all the data points line up. The next thing we're going to do is we're going to get this view into a um, flat projection so we can do analysis on it. Right now, like I said, it's the WGS global coordinate system. So it looks at everything in the world as kind of a globe, a sphere, and we need to get this projected into a flat surface. And so to do that, we're going to pick a local projection. This is in Minnesota, and a popular local projection in Minnesota is UTM NAD 83, and we're in zone 15. So there's where you can see where we are in the world. So we're going to hit OK, and what that does is it flattens things out and it puts everything into meter units rather than decimal degrees. Now what we need to do, we need to export these grids, these CSV grids as shape files, and we need to convert those to projected shape files. So I'm going to right click, we're going to go to export, save features as. We're going to save it to an Esri shapefile, and we'll put this in the temp folder. Call this, and call it UTM there. Save, and we want to make sure this is in that new projection. Okay, I think everything else is good. We want to add that save file to the map. So there we are. We can get rid of the CSV file now, that layer. Yes. We want to do the same thing now. Right click, export save features as. We want to do that same thing with the depth layer. Okay. Again, make sure it's projected correctly. Okay, there we go. Now we're going to get rid of this. The next thing we're going to do is I'll just have one of these highlighted just to make it a little less confusing. The next thing we want to do is we want to convert this to a raster. Raster grid, it's a different kind of GIS layer. And but what we need to know is how big of the grid cells do we need to create. So we're going to use the measure tool, and we're going to measure from here, from one point to the next, and you'll see, okay, so that's 10.3. It's not exact, and I think if we zoom in even more, we can get maybe a little more exact. 10.7, okay. It's all going to be around, okay, 10.9, okay. 11-meter grid cell should do it. If there's gaps in the grid cells, you might need to go a little bigger, but we'll try 11-meter grid cells. So now what we're going to do is we're going to create a raster depth grid. So go to raster. We're going to go to conversion of this point layer to raster. So we hit rasterize. And we're going to select depth for this field to use for a burn-in value. I'm going to select georeference units, and I said we want to do 11-meter grid cells. Oops. For now, we can just save it to a temporary file and then just see what happens. So run this. Looks like everything worked. Here's our scale from 0 to 31 feet. That seems about right. We hit close. Overall, the it looks right. You can see now here's it's turned it into a raster with those raster grid cells. So now we have our depth grid. Next thing we want to do, we can click that. The next thing we want to do is we want to create a, um, a biovolume grid. So we're going to do the same thing. Go to raster, conversion, rasterize, and the field we're going to use is biovolume. And again, 11, 11, and that. Oh, and then we want to select georeferenced units. Okay, I think That's it. We just save those as temporary. Hit run. And yep, it looks like, and the biovolume grid, it's on a scale of 0 to 1, or that's what that would be. So it expresses a proportion. 0 to 1, 1 is actually 100% biovolume, vegetation growing all the way to the surface. So that scale looks right. And we just hit close, and plays off. And for some reason, it doesn't create. This is an area, the deep area. It doesn't create grid cells of all those zero biovolume values, but this looks about right where the dense vegetation is, and that's the white here. We're not really concerned about the colors right now. We're just putting together. We're just going to now do. Um, we're just going to do some fun raster math. The raster calculator. Is a is just like a regular calculator, but it does map math. So the two grids that we're going to put together with the raster calculator, we're going to create a plant height grid. This is a really neat research data set that is quite unique to BioBase, the way we produce vegetation data. It's a three-dimensional view of vegetation, plant height. And to do that, biovolume is expressed from, it's a proportion of the water column occupied by vegetation. So if you simply multiply that by the depth, you're going to get plant height. So we go to a raster. So first thing we want to do is let's turn these depths from negative to positive. Let's turn off our um, biovolume map, and we'll turn on our depth map, and we're just simply going to turn these from negative depth values to positive. So we're going to go to raster calculator, bring this up here. Um, and tell you what, before we do this, let's rename these so we know what they are in that list. I right click, rename it. This is going to be BV. And then this is going to be rename. This is going to be depth. Yeah. Now we know what they are when we pull up the raster calculator. Okay, we're just going to go with depth, and we're going to multiply that by -1. And we got to save it. Let's just call this depth grid positive. Okay, save. And so now all those are positive values. And you know what? Let's get rid of this guy, so we don't need this anymore. Keep our layer dashboard here clean. All right, so now let's create that plant height grid. So go to our raster calculator. And all we need to do is take the depth grid, multiply it by BV. Rename it plant height. All right, so now this is our plant height grid. We have plants that range from essentially 0 to 8.65 feet long. It's pretty long plants. Um, and if we wanted to, we could maybe just color it. Something like this is maybe interesting, and we just hit OK, and then it just makes it a different color. So this is one maybe final data set that you might be interested in doing analysis on, and then this could be used for a variety of data analyses. If we want to take it a step further, maybe we want to figure out, where are those navigation hazards as boaters? Where is vegetation um, growing very close to the surface or where it's too shallow that we maybe want to avoid. And we can do that by creating a a depth to top of the plant canopy grid. So the next thing we're going to do is, so we have plant height and we have, so we just going to do a very simple calculation. Here's our depth grid, and we're just simply going to subtract plant height, okay? And um, depth to plant. Hit save and hit OK. All right. So, and so now we have that data. And the next thing, so this just shows here's a scale. 0 is going to be those areas that are either really shallow where the vegetation is growing to the surface. 25, um, that's 25 feet. That's going to be kind of there is no navigation hazard there. There's no plants or the plants are very low to the bottom. So one of the things that we're going to play around with here is what we want to do is really want to make these colors pop that are going to be 0 to, let's just say, um, 1.5 foot. So maybe that's the average draft for a boat. So we're going to let's turn this, these things are menus are very large, or make this a little smaller. Let's make this red. Actually, um, here's where you can alter those red, green, blue color values. Let's just make this red, and we're just gonna see, make that red, and then we're gonna make this guy red. Do the same thing. Okay, and now you know what? Let's just make these. Um, yeah, let's change this to maybe 2. And let's just make these completely transparent. So no opacity. We're just going to go down and we're going to do that for each one of these. Again, this is not something that's going to be publication quality, um, map. It's just something that's a little more visually um, appealing, and so where you can really see where maybe a navigation hazard is. Hit OK, and there it shows you where anything that's red, that's really where you're going to have these navigational hazards. It's either going to be shallow, or in this spot, it's not maybe necessarily shallow, but there's a lot of topped out vegetation growing. So there you go. That's a little hint on how to um, analyze biovolume data in perhaps a different way you've never thought of before. Thanks a lot.